Hello again, this is Mr. Vigil, and today we're going to be talking about one-variable inequalities. Okay, so before we get to that, let's just do a quick review of equations, specifically one-variable equations, which we did a whole bunch on with all those mystery numbers activities. Right? So equations are just basically statements that say two things are equal to each other. So for example, say we have 2 times x plus 1 equals, say, 5. Pretty simple equation. So equation is saying that two things are equal to each other. Inequalities are going to say that two things are, well, not equal to each other. Duh. So here's an equation. We can solve it. Solving means to undo what's being done to a variable. We have to undo the things in reverse order. So first, what's happening to x? It's being multiplied by 2, and then we're adding 1. So we have to first undo adding 1 by, of course, subtracting 1 from both sides. The whole point is that that's going to cancel out that adding 1, giving us 2x is equal to 5 minus 1 is 4. And then we just undo this multiplying by 2 by dividing both sides by 2. That's going to get rid of that. And now we're down to x equals 4 divided by 2 is 2. So there is the solved equation. We have x all by itself. Of course, we had that set notation saying that the solution set of the original equation consists of the number 2. And what we really could do if we wanted to, since we're in a one variable equation, we're on a one-dimensional space. So we're really just on the number line. We could graph the solution set here. Let's see here. Here's 0, here's 1, here's 2. So we're saying the solution set consists of just that point 2. So we just put a nice big dot on 2, and there's the solution set. Just that point. There we go. Of course, we saw how when we write linear equations, the solution set was a line, or we find one point when we solved a system of linear equations, there was a point in the coordinate plane because we had two variables, meaning it's a two-dimensional space. Here we're dropping back down to one variable and the one-dimensional case for just a little bit. We're going to go back up to two variables in the next class. So that's the basics there. I think we all got that. So now let's get over to inequalities. And there are various different ones. Like I said, well, an equation says that two things are equal. Inequalities say they're not equal. So one possibility for an inequality is this symbol here, which is an equal sign with a line through it. And that basically is saying that is not equal to. Hopefully you guys have seen this before. So for example, you might have the inequality of x is not equal to 2. Over here with the equation x equals 2, here's the inequality of x is not equal to 2. Okay. And of course, we could graph this as well. Again, one variable, so we're on a one-dimensional space, the number line. Here's 0, here's 1, here's 2. Now what we're saying is we want everything except for the number 2, or the point which we named with the number 2. So the way we show that, and we've looked at this before, if we don't want the point, we just put an open circle over that point. So we don't want the 2 because we leave the circle open. But we do want everything else. And we can't, obviously, like, put a dot on every single point here because, well, there's uncountably many points here on the line. But just to show that we want everything else, we'll want everything to the right of this point 2. So we're just going to shade the number line here and just say that we're going to, a little arrowhead, we're going all the way off to the right. But we also want everything to the left. So we shade the number line that way with a nice little arrow. And here's where colored pens or pencils are going to come in handy a great deal. Now, for these types of things, this point right here, the point 2 that we don't want, that's what we call a boundary point. Not really important bit of vocabulary right now, but the boundary of a set is really important, and eventually we're going to need to know about this. And so there are two different kinds of sets. This is what's called an open set, and the open set does not include the boundary. And we have what's called a closed set, in which we do include the boundary. Here we're not including the boundary, so this would be called an open set. It'll make a lot more sense when we start getting into higher dimensional spaces and why it's actually important. But, of course, this isn't the only inequality. I think you've seen all these other ones before. We have, of course, this symbol, which means is less than. But I prefer to think about this, I mean, is less than, when you start getting into absolute values and stuff, things get a little fishy. So if is less than, I prefer to say is to the left of. Because smaller numbers, of course, 0 is less than 2, 0 is to the left of 2 on the number line. Whereas if you went down here, say like -1, -2, -2 is still less than 1. Even though, well, in absolute value, the distance that -2 is from 0 is greater than the distance 1 is from 0. But what really matters is the position relative to each other on the number line. So that's one inequality. Then we also have this one, which of course means is greater than, or, of course I prefer, is to the right of. And I also like the directions, just because when we get into two variable stuff, now it's not just going to be left and right. Now we're going to have a y, which is going to be up and down. And so it's just kind of helpful. So this means is less than or is to the left of. This means is greater than or to the right of. But we also have this one, where we take the is less than symbol and we throw on a little half of an equal sign. And this one, of course, means is less than or equal to. Or, of course, we have this one, the greater than sign with a half of an equal sign, and that is greater than or equal to. And so, here we have, up here we had x is not equal to 2. 2 was the boundary point. The point where equality actually happens, that's the boundary. So these two symbols are going to be creating closed sets, while these two are going to be creating open sets. Because these two, we don't want to include the point where equality happens. These two, we do want to include the point where equality happens. Hopefully that's also a bit of review for you there. Now, the bigger part here is how to solve an inequality. I'll just go through a few examples to show you that actually, for the most part, it's the exact same thing as solving equations. So, example 1, let's try this. 2x plus 1 is less than or equal to 5. So let's just attack this like we would a regular equation and just start undoing what's being done to x. Here we got plus 1, so we're going to undo that by subtracting 1. And we've already done this most part, so we've got, of course, 2x is less than or equal to 4. Then we'll divide both sides by 2. And we now have x is less than or equal to 2. So we've just solved the inequality, meaning we've undone what was being done to the variable x. But, so this is a big set. It's an infinite set, an uncountable set. We want to graph the inequality. Again, on the number line, here's 0, here's 1, here's 2. It's less than or equal to 2. So we're going to include 2. So we're going to put a nice big circle there and shade it in to show that, yes, we do want the boundary point of 2, which is where equality happens. Now I want also all the points that are to the left of 2. So just shade to the left, put a nice little arrow there, and now we've graphed the inequality. So these are all the points that solve, or that are solutions to our original equation, or excuse me, our original inequality. But we might want to check to make sure we did this right, just in case. So we're just going to, all we do is just pick a point over here to the left of 2. 0 is always an easy point to use. So we'll check to see if 0 actually works. So we plug 0 back into the original inequality. 2 times 0 plus 1. We ask ourselves, is that actually less than or equal to 5? I simplify here. 2 times 0 is 0, plus 1 is 1. 1 is definitely less than or equal to 5. Yes. Good. Pretty simple, right? Let's try another one. Example 2. Let's try, say, 3x minus 5 is greater than 10. And sometimes I always say is strictly greater than, just to show that we don't want where equality happens. So again, we're just going to undo what's being done to the variable x in reverse order of operations. So first we're going to add 5 to both sides. (3x) is now greater than 15. We'll divide both sides by 3. And we have x is greater than 5. And there is our solved inequality. Again, we should graph this thing. Let's see, here's 0, here's 5, here's 10, say. Now this is a strict inequality, so we don't want where the equality happens, meaning at 5. So we're going to put an open circle there. But we do want everything to the right of that. So we just shade to the right, put a little arrow there. So we're not wanting 5, but we want every single thing to the right of 5. And I mean, as close as you want to get to 5, those points are included. I mean, even between 5 and 5.1, there's infinitely many more points. All of those are included. But we just want to check to see if we did this right. So we'll pick an easy point out here. 10 is pretty easy to work with. I like that one. So let's just check to see if 10 makes the original inequality true. So we plug that in. 3 times 10 in for x minus 5. And we ask ourselves, is that actually greater than 10? Well, 3 times 10 is 30, minus 5 is 25. Is that greater than 10? Yeah, sure is. So we did it right. So far, nothing has changed from solving equations. Let's do one last example just to throw a wrench into the whole thing. Example 3. Let's try, say, negative 5x minus 7 is less than 3. Let's just attack it the same way as we were doing before. Just undo what's being done to the variable in reverse order of operations. First, we'll add 7 to both sides, getting rid of that. So we have negative 5x is less than 10. Then we'll undo the multiplication by negative 5 by dividing by negative 5. And now we have x is less than 10 divided by negative 5 is a negative 2. Okay, so let's graph that solved inequality. Here's 0, here's negative 1, here's negative 2. It's a strict inequality, so we don't want to include point where equality happens, but now we want everything to the left of that. And there we go. But let's pick a point out here and check to see if we did it right, just to be sure. Negative 10 might be an easy point. So we'll ask ourselves, is negative 5 times negative 10 minus 7 actually less than 3? Let's see here. Negative 5 times negative 10 is positive 50. Minus 7 would be 43. Is that actually less than 3? No. So the question is, what went wrong? Well, it's actually a pretty simple thing to see. Show with a really simple example here. Just pick two numbers, I don't know, 5 and 10. 5 is most definitely to the left of 10 on the number line. All right. So let's see what happens when we maybe add something to both of them. Why not 2? 5 is less than 10. 5 plus 2 is 7. 10 plus 2 is 12. And yeah, 7 is definitely still to the left of 12. No big deal. Something is less than something else. We add something to both of them. The result on the left is still less than the result on the right. Let's try maybe subtracting 2. I don't know. 5 is less than 10. Sorry about the bell. Subtract 2 from both sides, and we have 3 and 8. Oh yeah, 3 is definitely still less than 8. No problem there. 5 and 10. Let's try multiplying by 2. Why not? 5 times 2 is 10. 10 times 2 is 20. Yep, still perfectly fine. Maybe dividing. Let's try that. Because we did do a division over here. 5 is less than 10. Suppose we divide both things by 2. 5 divided by 2 is 5 halves, or for this purpose, kind of makes sense to say 2.5. 10 divided by 2 is 5. Yep, 2.5 is still less than 5. Again, no problem with any of those things. The problem that occurred back here was we are actually dividing by a negative. So that's an issue. Subtracting or adding a negative, no problem here, but we have 5 and 10. If we multiply both of them by negative 2, 5 times negative 2 is negative 10, and 10 times negative 2 is negative 20. But negative 10 is most definitely not to the left of negative 20. No way. Right? Here's 0, here's negative 10, here's negative 20. Negative 10 is to the right of negative 20. So here's one of the ideas. When you're multiplying both sides of an inequality by a negative number, what happens is the inequality flips. Or 5 is less than 10. If we divide both things by a negative number, well, now we have negative 2.5 here. 10 divided by negative 2 is negative 5. Here's 0. Here's negative 5. Negative 2.5 is right there. Negative 2.5 is most definitely to the right of negative 5. The inequality flips. That's the only thing that changes from solving equations. If you multiply or divide both sides of an inequality by a negative number, you have to flip the inequality around. So let's redo example 3. Negative 5 times x minus 7 is less than 3. First we add 7 to both sides. That's not a problem. Negative 5x is now less than 10. Now we divide both sides by the negative 5. But now, since we did that, I don't know, we might want to put a big box and some stars around here or something saying, flip that darn thing now. Don't forget that. Now we have x, we flip it around, is greater than negative 2. And that's our correctly solved inequality. Of course, we can graph this to show the entire set. 0, negative 1, negative 2. We don't want the point where equality happens, so we put an open circle there. But we do want everything to the right. And we might check it again. Pick an easy point out here. 0 is always easy. Plug that back into our original inequality. Negative 5 times 0 minus 7. Is that actually less than 3? Well, let's see here. Negative 5 times 0 is 0. Minus 7 is negative 7. And negative 7 is most definitely to the left of 3. Totally fine. Just always remember, if you're going to multiply or divide both sides of an inequality by a negative number, you have to flip the inequality. Okay. That's pretty much it for solving one variable inequalities. Thank you for your attention. And, well, hey, go enjoy yourself an icebreaker mint. They're very refreshing.